All right, guys, let's go ahead and get started. So we've got our last real lecture today. So today we're going to continue our lecture on load, shear, and moment diagram. So if you recall, or if you look back at your notes, you'll see that when we left off last time, we were starting example 3. In example 3 here, we had a point load as well as a uniform load on this entire beam. And before we left last time, we had solved for the reactions at A and C for this beam. So we were ready to start the shear and moment diagram part of this problem. So I've recopied that here. And so today we're going to just work through the shear moment on this one. A couple notes on grades. I just realized somebody pointed out that homework 5 has been graded for a while, but for some reason the assignment grades are muted in Canvas, and I can't figure out how to unmute it. I think it looks like a Canvas problem. I'm going to work on that though to get those grades unmuted so that you can see those. And then the rest of your grades will be completed by Monday at the absolute latest. Your test will be completed by Thursday. So we'll go over the test in class on Thursday. Those are almost done. So we'll go over that before we start to review and talk about the final exam Thursday. Any general questions before we get started today and continue talking about load, shear, and moment diagrams? Okay. So we'll follow the same process that we did before. You know, we're kind of working through these problems differently. We can't really say that we have a set process. We kind of have a set, somewhat of a set process in how we go about starting the problem, but depending on what the loads look like, you know, each problem looks different. So basically, once we know how to handle point loads on shear and on moment, and once we know how to handle uniform loads, then we can work all of these problems just with the different combinations. So step 1 will always be, unless we're given those support reactions, to find those support reactions. The next thing, you know, we want to show those support reactions on our load diagram. And then we will draw our dashed lines, you know, on the left hand and the right hand side of our beam to create sort of the margins, the starting and the stopping place for our shear and our moment diagrams. And then any place that there's a point load, that will typically be a point of interest as well. So when we have a point load here at B, I'll go ahead and draw a dashed line there as well. And with this problem having a support with a cantilever portion instead of having the support at the very end, we know that the support has a point load here, so that's going to produce another jump in our shear, so we'll draw a dashed line there. If you don't draw your dashed lines correctly to start with, that is not a big deal at all. But sometimes you can look ahead and see where these points of interest are going to be, and just kind of help you line your drawing up. All right, so we want to create basically our shear equals 0 line. Okay, so this is our shear diagram. This is the location where shear is equal to 0. Shear is showing that change in applied force on our beam. So we start and we end at 0. So we'll start here, shear equals 0. Since we have a 1,200 pound point load, it's the support reaction, but that represents a point load for this case. We're going to jump up. So positive is in the up direction. So we'll jump from 0 up to a positive 1,200 pounds for shear. again, when we lay out these kind of points of interest with the dashed lines, that kind of helps us see with this semi-graphical method, we're not looking at each individual location on the beam. We're kind of taking a more big picture approach to it. So we know that there are no point loads between here and here. So we're going to basically find out what happens between here and here and then graph that. So for this 7-foot section of beam here, we have this uniform load of 200 pounds per foot. So we've got 200 pounds per foot applied over that 7-foot section. Okay, and that is going to be a negative, right? That load is applied down. So when we look at negatives and positives on shear, we're just looking at the direction either up or down for our loadings. So that's a negative here. So this will be a negative 1,400 pounds. Right, so we start at 1,200 pounds. We decrease by 1,400 pounds. So that puts us at negative 200 pounds. Okay, so we're looking at what's going on here to here. So we start at 1,200 pounds. We decrease by 200 pounds per foot over this 7-foot portion of the beam. And so that puts us here at negative 200 pounds. Okay, so that's going to be a straight line. You can use some straight edge if you have it to show that straight line. All right, so at this location, we have a point load of 1,200 pounds, okay? So we're starting at negative 200 pounds. We're decreasing by another 1,200 pounds. Okay, so that's going to put us at a negative 1,400 pounds. So we start at negative 200, we go down, there's a jump here down of 1,200, and that puts us at negative 1,400. Jump straight down like that. All right, for the next 3-foot portion of beam, we have uniform load only, no point loads. Okay, so we've got another 200 pounds per foot. Over this 3-foot portion of beam. Okay, that's still applied downward, so that's negative. So that gives us negative 600 pounds. So we're starting at negative 1,400. We're decreasing by 600. So that gives us negative 2,000 pounds for our next point. So from here to here, we go to negative 2,000. Again, that's a straight line. All right, so now we're at negative 2,000. We have a point load of 2,800 pounds here. Going up, so negative 2,000 plus the 2,800 pound point load gives us 800 pounds positive for this point. So we go from negative 2,000, we jump up by 2,800 That puts us at a positive 800. And for our final 4-foot section of beam, we still have the uniform load. So 200 pounds per foot. Apply downward, so negative. Times 4 feet gives us negative 800 pounds. Okay, so we start at 800. We decrease by 800. So that puts us closing at 0, which is what we want. So again, this will look like a straight line. So essentially, when we have a point load, that point load will look like a jump. So it'll be a line either going up or down on our shear. And when we have a uniform load, that typically looks like a triangle on our shear. Okay, any questions about the shear diagram for this problem? Okay, you can kind of see that the moment diagram will take some work because there's so many different little areas here. So let's take a look at the moment diagram. So I'll zoom out just a little bit so we can see everything. All right, so our moment diagram, we'll draw another line here to represent moment equals 0. And we want to look at each area separately. Okay, so we've got the first area here, which will be positive. We've got this location where we cross the x-axis. We know that'll create a different point on our moment diagram, so we can go ahead and draw a line there. The second area here will be negative. Our third area here will be negative. And our fourth area is positive. Okay, so when we look at negative versus positive areas on our shear diagram, we're just noting whether it's above or below the shear equals 0 line there. All right, we want to figure out this distance. Okay, so let's call this distance x. Okay, we had the formula before where we start with our beginning point, 1,200 pounds, so 1,200. Subtract our uniform load, which equals the slope, so minus 200x. We're looking for the location where that equals 0. So y equals mx plus b is the basis of this. When we solve this, we get x equals 6 feet. So this is 6 feet. So that leaves us with 1 foot for this distance. Okay. All right, I'm going to use a separate sheet to do these calculations. Since we're running out of room. All right, so our first area is triangular. Call that area 1. Since it's triangle, it's 1/2 times the base, which is 6 feet, times the height, which is 1,200 pounds. Okay, so that gives us 3,600 pounds times feet for our first point. All right, so on our moment diagram, we start at 0. And then we go to positive. This is a positive area. So we go to a positive 3,600 pounds times feet. Okay, so when we have a uniform loading, like we do here, that shows up as a triangular loading on our shear, and it shows up as that curve, second degree curve that we talked about on our moment diagram. Okay. Our next area is also triangular. So we've got the area of our second triangle here. This is a negative area, so we'll have a negative 1/2, base of 1 feet, height 200 pounds. So you can either count the negative up front by recognizing it's negative, or you can just put in the negative 200 pounds here to make sure that that's a negative area. Okay, so 1/2 times 1 times 200 gives us a negative 100 pounds times feet. Okay, so we're starting at 3,600. So we start at 3,600 pound feet. We subtract area 2, which is 100 pound feet. So that gives us 3,500 pound feet for this point. So our second point here will be a positive 3,500 pounds times feet. And that will be also a second degree curve. Okay, any questions so far about the first 2 points here? So basically when we have a point load that creates the jump like we see here, and we split these two areas up, okay? The first one looks like a triangle, the second one, or what we've called area 3 here, is everything under the curve. So you can see we've got kind of a more complicated geometry going on here. But when we look at area 3, this is what we're looking at. So everything under the curve all the way over to our 2,800 pound point load here. Okay, so all of this. So when we have a situation like this, the easiest way to handle it is to break it up into sub areas. So basically we've got a rectangle plus a triangle here. So if we kind of create this little separation. Okay, now we have a rectangle here, we have a triangle here. So it's something that we can solve now. Okay, so let's call this area 3A. We'll call this area 3B. All right, both of the areas are negative. Let's start with 3A. Okay, so we know this is 3 feet. And just by lining that up with our load diagram, it's 3 feet. So area 3A. Since it's a rectangle, it's just base times height. So 3 feet times 1,400 pounds negative. Okay, so that gives us negative 4,200 pounds times feet. Okay, area 3B. Okay, so what we have here, let's just sketch this a little bit bigger so we can look at this. This is 3B. All right, so for 3B, this point, negative 1,400 pounds, right? This point here. And then this lower point is negative 2,000. Okay. And this distance is still 3 feet. Okay, so if this is negative 1,400, this is negative 2,000, what's the actual height of that triangle? Good, 600 pounds. So that's the tricky part, I think, when we have the multiple shapes combined. At least what seems to be the tricky part for a lot of people is realizing we just need to subtract these. Okay, so this is negative 2,000 times 1,400. So the actual height here, 600 pounds. It's still a negative area. And this is still 3 feet. So to get the area of 3B, just 1/2 times 3 feet times negative 600 pounds. So that is a negative 900 pounds times feet. Okay, so we've got 3A plus 3B. So that's negative 4,200 minus 900. Okay, and you don't always have to write it out in such great detail, but I want to walk through it that way so that you guys are comfortable. Okay, so 4,200 minus 900 gives us a negative 5,100 pound-feet. Okay, so again, we start at 3,500 here, positive 3,500 pound-feet. We subtract 5,100 pound-feet. So that gives us negative 1,600 pound-feet for our next point. Okay, so our next point here, we're going to have to go below the zero line here to negative 1,600. Still a second degree curve, so we got to kind of connect these and just show that second degree curve there. And then our last area, area 4, is positive. Okay, this is a 4-foot distance. So area 4. It's triangular, so we've got 1/2 times 4 feet times 800 pounds, all positive. Okay, so that gives us a positive 1,600 pounds times feet. Okay, so we started at negative 1,600. We add 1,600. So we close at 0. Okay. Again, it's always a good check with shear moment diagrams to see if we close back at 0 like we should. So we close here at 0. And it's a second degree curve. So we'll show that like that.
How was it that we chose whether it's a concave or a convex curve again?
Yeah, so that's a good question. So the way that we decide how the curve looks, whether it's basically up or down, is based on the way that the uniform load is applied. So for us, we make it easy because if the uniform load is applied upward, then it's going to curve the other way, basically a smiley shape, right? And then if it's applied down like we have here, it's going to be curving down. And so since in reality, it's almost always uniform loading applied like we see here, we're always going to have, just for our problems, these are curving down. If we had a situation where the uniform load was applied in the other direction, that would look the opposite, right? But again, we just don't see that a whole lot in real life, so I don't really do any problems like that. I try to mimic, what's really happening in reality. That's an excellent question. So for us, for all the problems that we'll see in class, we always want to make these second degree curves curving downward. Good. Any other questions about this problem or about load shear moment diagrams in general so far? All right, let's work through another example together, and we'll do an in-class example for you guys to work here. Okay, so this will be our 4th example. Okay, and this will just be a little bit different combinations of loading. Again, once we figure out how to handle point loads and figure out how to handle uniform loads, the process will just be applied the same way every time. So let's have a simple beam here. Pin at A, roller at B. So at 10 foot from A, we'll have a point load of 15 kips. And then 20 feet. We're going to have a uniform loading here. So the uniform load's applied over this 20-foot section. And that's going to be equal to 3 kips per foot. Okay. We know how to figure out support reactions at this point, but I'm going to go ahead and just give those to you here to save time. AY is 30 kips. BY is 45 kips. Okay, so for any of these problems that we don't can solve the uniform loads, point loads into support reactions together, it's a good chance to go back and get some practice with those since you know the answers. All right, so this represents our load diagram. We want to go ahead and draw our vertical dashed lines here. Okay, we've got this point load, 15 kips. We'll draw a line there because we know that that will represent a change on the shear diagram. And then the right side here as well. Go ahead and draw that dashed line. Okay. So we've got a horizontal line here for shear, where shear is equal to 0. So we'll start at 0. We're going to have a jump to 30 kips. Okay, so this jump represents that support reaction, 30 kips. Okay, between this 30 kip jump and the 15 kip point load here, we have no uniform load. We have no other point loads. So for this section of the beam, the shear will remain constant. So that will look like a flat line. When we get to the 15 kips, okay, we'll jump down by 15 kips. So we started at 30. We'll jump down to negative, or jump down to a positive. We'll jump down by 15, so 15 kips. Okay, so we start at 0. We jump up by 30 kips to represent our support reaction. The shear stays constant across the beam. We decrease 15 kips, so we end up here. Okay, so now we've got this 20-foot section of beam where we have a uniform load of 3 kips per foot. So we've got 3 kips per foot over a 20-foot section. And that load's applied downward, so that's a negative. So that gives us negative 60 kips. So we start at 15 kips, subtract 60 kips. That puts us at a negative 45 kips. All right, so we start at 15, and then we're decreasing by 3 kips per foot across this 20-foot span. And so by the time we get here, we'll be at a negative 45 kips. Okay, that's going to be another straight line connecting these two. Okay, and then we're at negative 45. We can see that we've got a jump of positive 45 here at B for the support reaction. So we go from negative 45 up 45. And so that puts us closing at 0. Okay, questions about this problem so far? All right. So let's look at the moment diagram. So this is a moment equals 0 line. And we've got 3 areas here. Area 1 is positive, area 2 is positive, and area 3 is negative. Okay, so area 1 is rectangular. Again, it's positive. So we've got base of 10 feet. Going back to our load diagram, we know this distance is 10 feet. So our area is 10 feet times 30 kips. So that's 300 kip feet. Okay, we start at 0. And we increase to a positive 300 kip feet. All right, this is a rectangular area. So do we have a 1st degree or 2nd degree curve here connecting the two? 1st degree being a straight line, 2nd degree being the arch. So the easiest way to remember, if it's a rectangular area, then we've got a 1st degree curve, which is a straight line. If it's a triangular area like we have here, then we'll have a 2nd degree curve. All right, so we need to get our distance x here, where we cross the shear equals 0 mark. So we start at 15 kips minus our slope, 3 kips per foot, times x equals 0. Again, this is following the y equals mx plus b, which we derived last class. We talked about this. And that gives us the point where this line crosses the x-axis. Okay, so that gives us x equals 5 feet. So we got 5 feet here. That leaves us with 15 feet here. Okay, so now we can get area 2. Area 2 is triangular, so we've got 1/2 times the base 5 feet times the height 15 kips. Okay, that's positive since it's above the line here. So that gives us 37.5 kip feet for area 2. So we start at 300. We increase by 37.5. So that gives us 337.5 kip feet for our 2nd point. Okay, so again, when we cross the x-axis, we'll show that as a dashed line too, because when we cross the x-axis, that means we go from either a positive to a negative or a negative to a positive area. So we have to show that change there. So we've got 300 kip feet. We increase by 37.5. So that puts us at 337.5 kip feet. Okay, and so this is a triangular area. So this will be 2nd degree curve. Okay, and again, this is a 1st degree. All right, our last area, area 3, is negative. Okay, so area 3, 1/2 times 15 feet times negative 45 kips. Okay, 1/2 base times height, knowing that it's negative. Okay, that gives us negative 337.5 kip feet. Okay, so we started 337.5. We decreased by that amount, so we end up at 0. Okay. So this will also be a second-degree curve, since it's a triangular area on our shear, which means it's a uniform loading on our load diagram. Any questions about this problem? All right. All right, let me give you guys a practice problem to do now. In-class problem. Okay, that will have point loads and uniform loads here. All right, so we'll have a roller at A, pin at B. We'll have a uniform load applied on half of the span between A and B. So this load is 2 kips per foot over a distance of 8 feet. So we've got another 8-foot span here. 6-foot cantilever portion here with a point load of 4 kips applied at the end. Right, and I'll go ahead and give you guys the support reactions here. AY is 10.5 kips. And BY is 9.5 kips. Okay, so you want to draw the shear and moment diagrams using this load diagram. Okay, so we'll work this in class for the next few minutes and then go over it together at the end of class. right, guys, let's go through the solutions here for this problem quickly. So for shear, we want to start at 0. We'll jump up to positive 10.5 kips. I'm going to go through the without doing all the calculations first. That way you guys will have a starting point for checking your work. And then if you need further details on the calculations, we can look at that. So we start at 0, we go up to 10.5 kips. We're going to decrease by 2 kips per foot over this 8 feet. So starting at 10.5, we're going to go down 16. So that'll put us at 5.5 negative. Okay, that's going to be straight line. Okay, so between this point and our 9.5 kips here, we have no change in shear. So it'll be flat. We go from negative 5.5 up 9.5. So that puts us at a positive 4 kips. Between this point and the end, there's no change. So we start at positive 4. We're going to go down by 4. So that puts us closing out at 0. Questions about that? Okay. So again, if we do the math here, we get 5.25 feet for this distance X, which leaves us with 2.75 feet for the remaining distance. So moment, we should start at 0. We're going to note the place where this crosses the x-axis. Start at 0, we increase to 27.6 kip feet by taking the area of our first triangle, area 1. We subtract area 2 from that, and it puts us at 20 kip feet. Both of these are going to be second-degree curves. Take the area of the third object here, which is a rectangle. Subtract it from here, we get to negative 24 kip feet. So since that's a rectangular area, it's going to be a first-degree curve here. And then we take an area of the final rectangle, area 4, we close out at 0. So we'll connect that with the first-degree curve as well. Any questions on the moment diagram? All right, so what I'll do for shear moment diagrams is I'll post some extra problems in case you guys want to practice that. Instead of making a graded homework, it'll be kind of an optional homework for you. But typically, you know, everybody does pretty well on shear moment diagrams overall in this class. So we'll do that. I wanted to end my lecture a little bit early because I wanted to ask you guys, I know you've probably been getting a ton of emails about the course evaluations and stuff. But I want to tell you, really tell y'all how important that is, like to me, for a couple of reasons. Number one, it's important for, me staying around to teach and everything like that. I want to know what y'all think. Like, I want to know what you think is going well. If you think something is not going well, I want to know that too. But both the number scores that you rate everything for, that along with the comments, especially the comments, are super helpful. That's probably the most helpful thing, just to get some good feedback. I'm sure y'all know it is completely anonymous. I won't even see like what the results of those surveys are until after the semester. But with them being electronic, if y'all don't participate, it's really hard to get feedback. Like if I just have 4 or 5 people, it's not a good representation of the whole class. So it would be super helpful, and I would really appreciate it if you guys would take a minute to fill that out. So I wanted to leave a little bit of time because I think it probably doesn't take but about 5 or 10 minutes to do. So I wanted to use this last part of class to do that. So I'll go ahead and end the recording.